Hold on. Okay, you can start now.
Thank you. Welcome everyone to today's seminar. It's a pleasure to introduce Yara Jaffe, who is a staff member at the Universidad de Valparaíso in Chile since 2018. Yara studied physics at the Universidad Simón Bolívar in Caracas, Venezuela, and obtained her bachelor's thesis in SIDA, Mérida, Venezuela in 2007. Yara completed her PhD in 2011 at the University of Nottingham in the United Kingdom, with a sandwich period at ESO, Germany. She held postdoctoral positions at the Osservatorio Astronomico di Padova in Italy, then as a Fondesit Fellow at the Universidad de Concepción in Chile, and as an ESO Fellow in Santiago, where she worked operating YEPUN, and as a MUSE Instrument Fellow. Thank you so much, Yara, for accepting our invitation. Looking forward to hear your talk on one of the most beautiful types of galaxy transformation. You may start when you're ready.
Thank you very much, Anna, for the invitation to give this talk virtually over there. I hope one day I can go in person. And yes, indeed, today I'm going to talk about galaxy evolution as a function of environment. So how galaxies transform and evolve with the universe as the universe transforms and evolves. And I'm going to have a particular focus on a very special kind of galaxy called jellyfish galaxies that are snapshots of galaxies transformations at play, and thus can teach us a lot of the physics that goes on inside of galaxies as they transform and evolve. So to understand the evolution of galaxies, we need to understand the evolution of the universe first. So the universe, our universe, we think it's a hierarchical universe where the structure grows and evolves over time. So here I show cosmological simulations showing the evolution of the density from the early universe at high redshift out to today. And you can see that in the early universe, the universe was quite homogeneous. There were only small anisotropies that grew with time and built up the most massive and large structures that we see today, which are massive galaxy clusters, filaments, and galaxy groups, which you can see here on the right. And what does this mean from the point of view of the galaxy? So from the galaxy's view, their environment evolves with time, and in general, it becomes denser as the universe evolves. So galaxies are not always in the same environment. Their environment will change over time, and this has to have consequences in their lifetime. And in fact, if we look at the distribution of galaxies across the cosmic web, this is again a cosmological simulation showing the distribution of mass in the universe. And we have these very dense regions where we can have hundreds or thousands of galaxies binded together by gravity. And in these places, we're much more likely to find elliptical and smooth galaxies in general. And if we go to the emptiest regions of the cosmic web, we're going to find galaxies that are very different to the ones that we find in clusters. We find galaxies that are spiral, that have a disk morphology, and are forming a lot of stars, okay? So this finding can be summarized by the very well-known morphology density relation shown here, where we have the fraction of different galaxy populations plotted against galaxy density, and we have that the higher the density, the higher is the galaxy density, the more likely you are to find elliptical and lenticular galaxies, and this growth happens at the expense of spirals and irregular galaxies, which are much more common in the field and low density regions of the universe. Now, the morphologies of galaxies also are connected with the internal properties of the galaxies. So elliptical and S0 galaxies, which are shown here in this morphology diagram called the Hubble fork, where on the left side, we have early type galaxies, which the main characteristic is that they're red, passive, and they're not really forming stars. And the reason why they're not forming stars is because they don't have the fuel to form stars. They don't have any gas from which to form stars. And on the right-hand side, we have star-forming spirals with and without bars, and also irregular galaxies. And as opposed to elliptical and lenticular galaxies, the spirals and irregulars have a lot of gas, a lot of fuel from which they can form new stars, and they have a blue appearance. And in fact, galaxy morphology is very tightly related to color. As I showed here, this example of the well-known color bimodality of galaxies, where when you plot the galaxy color with respect to galaxy mass, you find a very tight correlation called the red sequence for early type galaxies. And below this red sequence, you find all these star-forming spirals and irregulars in the blue cloud, and not so many galaxies in this transitioning zone, which implies that there is a mechanism that is transforming galaxies from the blue cloud into the red sequence. And it's probably relatively quick because we don't have that many galaxies in this transition zone. And in terms of the timescales of this transformation, if we look at galaxies at different redshifts, what has been found is that right about redshift of between 1 and 2, we start seeing this quenching of star formation in galaxies going from blue to red in color, and also galaxies going from spiral to elliptical and zero in morphology. Okay, and these relations, the color bimodality and the morphology density relations, are established around this redshift. And this is, it coincides with the epoch in the universe where these massive clusters are really virializing and are becoming very well-defined structures. So what I want to talk about in this talk is how this transformation from gas-rich star-forming disky galaxies go into passive gas-poor early type galaxies, okay? And there's essentially two things involved in the quenching of galaxies, as this diagram here from Peng et al. 2010 shows. And the two things are the intrinsic properties of galaxies and the environmental situation of the galaxies. So in this plot, what is shown is the fraction of passive red galaxies, okay, from the Sloan Digital Sky Survey in the color bar, as a function of galaxy density on the y-axis and galaxy mass on the x-axis. What we can see is that the more massive the galaxies are, the redder they become. But for galaxies that are less massive than, somewhere a bit less than 10 to the 11 solar masses, we have that environment really drives the quenching of the galaxy. So it really depends which environment they're in, if they're going to be quenched or not. So in this field, there is talk about mass quenching and environmental quenching. And mass quenching refers to galaxy evolution driven by internal properties of galaxies. For example, for massive galaxies, you have the effect of the big, massive, supermassive black hole in the center, called an AGN, an active nuclei, that can generate feedback and can help to quench and regulate the star formation of the galaxy. And in addition to that, we have the environment where these galaxies lie, and this environment will also drive different physical processes that I'll explain in a bit that can help quench the galaxies. So it's a matter of a mixture between nature and nurture. But if we have to narrow it down to one thing that drives galaxy evolution, I would summarize it in one word. It's all about the gas. It's all about the fuel to form stars. So in this diagram, we can see that the cycle of gas in galaxies is a quite complex process. We have gas accretion from the cosmic web. We also have recycling of the gas in outflows driven by the AGN and also supernova winds. And in addition to that, you have an environment that is able to remove or disturb the gas content within galaxies. So if you know what's happening with the gas in the galaxy, you know whether it's going to keep forming stars or it's going to die. So in this talk, I'm going to focus mostly on the environmental side of things, okay? although they're not completely disconnected, as you will see in some of the results I'll show. And in terms of environmental effects on galaxies, you can mainly separate them into two main categories. You have gravitational interactions, and any tidal gravitational interaction in galaxies will affect not only the stars in the galaxy, but it will also affect the gas. It will affect all the components that have a mass. On the other hand, you have hydrodynamical interactions, which only affect the gas, the hydro. And of course, in many cases, you have both things happening at the same time, if the galaxy is really unlucky. So in gravitational interactions, the most obvious interaction you can have is interactions between two galaxies. You have galaxy mergers. When you merge two spiral galaxies, for example, two gas-rich spirals, we know from observations and simulations that you can end up having a big, massive elliptical galaxy. And during this merger process, you can compress the gas, have bursts of star formation, and you consume all this gas that you had in these galaxies originally. And at the end, you will have a gas-poor elliptical. Here, I'm showing just one of many examples in the literature of a simulation of the star formation history and the amount, the gas mass in the core of the galaxy for a gas-rich merger. So the different color of the lines correspond to different orbits of the merger, different impact parameters. And here you have the distance from the two galaxies as a function of time. So this is where they get the closest, and then they kind of bounce back and forth until they end up merging. And if you look at this plot, you see that the amount of gas that flows into the center of the galaxy grows over time. And this means that you have a lot of central star formation happening because of the merger. And in fact, if you look at the right-hand side plot, you have that the star formation rate evolves over time with peaks that are pretty much coincident with the closest passage of the galaxies. So this is one way that galaxies can evolve. It's a quite violent process, of course. Other kinds of gravitational interactions can happen, for example, in big, massive galaxy clusters that can have thousands of galaxies. These are very massive systems, mostly dominated by dark matter. Okay, so galaxies only compose 1% of the mass of a cluster. And in these systems, the gravitational potential is so big that galaxies go very fast. And they go so fast that they're very not likely to merge. What they do is that they fly by each other at very high speeds, can be thousands of kilometers per second. And the accumulation of many high-speed encounters can disturb the galaxies and can thicken their disks and mess up their morphologies and so on. So that's called galaxy harassment. And you can also have the interaction between an infalling galaxy and the whole gravitational potential of the cluster. That is another tidal interaction, and that can affect galaxies falling into clusters. But if we go to the hydrodynamical interactions, we have that in galaxy clusters, not only we have galaxies and dark matter, but we have another component, which is called the intracluster medium, which is very hot gas that fills the space between galaxies. And we can see it in X-rays via thermal Bremsstrahlung, and it accounts for about 4% of the total mass of clusters. Infalling galaxies will encounter this intracluster medium and will feel the effect of the gas in the galaxies interacting with the gas in the cluster. This interaction can be thought of as the effect of a wind, because the galaxy falls at a certain velocity, and as it interacts with this intercluster medium, it will feel a wind that can blow away the gas that the galaxy has with it. And as I hope you saw in this simulation below, this process can essentially remove the gas in the galaxy, creating these beautiful tails that give the name to the so-called jellyfish galaxies. So this process is called ramp pressure stripping, and it essentially occurs, the condition for ramp pressure stripping to occur is when the ramp pressure exerted by the intercluster medium supersedes or overcomes the galaxy's ability to retain its gas, so the galaxy's anchoring force. So RAM pressure can be characterized by two parameters, quite simply. So the density of the intercluster medium, which we can derive from X-ray observations, and the square of the velocity of the infalling galaxy, which we can derive from the redshift of the galaxy. Of course, that's a line of sight velocity, but it's a projected velocity essentially. And in terms of the anchoring force of the galaxy, we can model it by assuming a certain mass density for the gas and the stars, for example, a disk profile. So there's a lot of work that has been done in the last few decades on RAM pressure stripping. So here I show one of a billion simulations of RAM pressure stripping at play, just to show you that RAM pressure stripping is a purely hydrodynamical process where what you strip is the gas, not the stars. The stellar disk of the galaxy, which is shown here by the white contours and colored contours at the center, corresponds to the stars. And here you have a density scale. And the green extended disk corresponds to the gaseous disk. And before the galaxies fall into the cluster, they have very extended gas disks that we observe in H1, as I'll show in a second. And as the galaxy falls into the cluster, it encounters this wind, and it will strip out the outer parts of the disk first. And as it keeps falling into the cluster's potential, it will strip further in the disk. Okay, this is what the simulations predict, because it's much easier to remove gas from the outer parts of the disk that have less ability to retain the gas. Okay, so you strip gas, but in some of the stripped gas, you can compress in not some of this gas, and you can actually form new stars. And this is something that we have observed, and you will see later in the talk. In terms of observations, the first really crucial observations of RAM pressure stripping at play came from radio, so from H1. So this is one of the most beautiful examples. This is the nearby Virgo cluster, where A.D. Chung led a study through the VIVA survey, where they mapped the H1 around many galaxies in this around this cluster. So here on the left, you have in yellow the X-ray emission of the Virgo cluster. So this is the intercluster medium essentially, and the different colors correspond to the H1 detected galaxies. These have been magnified by a factor of 10 so that you can see them. And the beautiful thing is that in the outer parts of the cluster, you have these very extended disks, but as you go closer to the cluster, these disks become quite smaller. And you actually see some of these RAM pressure strip features that I show here on the right a bit better. So here on the right, you have 4 examples, 4 Virgo galaxies. The background images are optical images, where we can appreciate essentially the stellar distribution of the galaxies. And the white contours correspond to the H1 gas from radio observations. And you can see that while the stars are unperturbed, that you cannot see any disturbance in the stars, the H1 contours are really clearly disturbed to one side. And that's one of the signatures of RAM pressure stripping, that any disturbance is one directional, because there is a one directional wind blowing the gas away in these galaxies. If it was a merger rather than RAM pressure, you expect to have not such a one-sided feature, and also you expect to have stars and gas disturbed, which is something unique about RAM pressure, that you only see the gas. So we've done, I'm going to show different results from different works that have been involved regarding RAM pressure and what we've learned so far in terms of how efficient this effect is. So one of these studies that I did a while back now comes from the deepest H1 survey to that date, which is called BUDDIES, the Blind Ultra Deep Distant H1 Environmental Survey, where we looked at H1 in and around galaxies in distant clusters, in 2 distant clusters, a redshift of 0.2. That's distant for H1 astronomy. And this is one of the clusters, Able 963, and this is plotted in right ascension, declination, and redshift as a 3rd dimension, although it's a velocity. And as you can see, all the cluster members are the red dots, and the H1 detections are grouped in the outskirts of the cluster, which are the blue boxes here correspond to the H1 detections. So confirming what we saw in the local universe, that gas-rich galaxies are outside the cluster, and as you go inside towards the dense intercluster medium, you stop having gas in the galaxies because this has been stripped. But what we wanted to do was to date this effect. So how efficient is run pressure and how long does it take to remove gas from galaxies? So to study this, we use a kind of diagram that is called the projected phase space diagram that I'm going to explain for those of you that have never seen it before. So on one axis, you can plot the distance from each galaxy to the cluster center. And on the y-axis, you have the relative velocity of each galaxy with respect to the mean velocity of the cluster. So if you plot all the galaxies within a virialized cluster in this kind of diagram, which are the crosses here, this is of course a made-up cluster by me, a cartoon version of a cluster, you have something that looks like this, a virialized system that lies below this line that corresponds to the escape velocity of the cluster. Now, if you have a galaxy entering this cluster from the very first time, you expect that the galaxy comes from a very large distance, okay, from far away, and as it gets closer to the cluster, because of the gravitational pull, the galaxy will gain velocity passing pericenter, and then it will bounce back, okay? This is shown here with the red line. This is very exaggerated just for the purpose of illustration, but basically you pass pericenter, which is the closest approach to the core, but gaining a lot of velocity, then you come the other side of the cluster and you keep bouncing back and forth, but each time with less velocity, essentially because of a combination of dynamical friction and violent relaxation. But what I want to say here is that basically, although what we have are projected distances from the cluster center and projected velocities, because we observe the universe in a projected way, we don't have the 3D information. Despite these projection effects, we can use this diagram statistically to infer how long the galaxies have been inside the cluster. So galaxies that are in this blue region that I paint here are falling into the cluster kind of recently, and the galaxies that are in this red region here have been in the cluster for a very long time, or more than a few passages, roughly speaking. We can, of course, do this much more carefully with simulations, and I quote here some papers where this has been done. But the one thing that we wanted to look at was, where is run pressure stripping in this orbital history of the galaxies? At which point in the orbits of galaxies do they get stripped? So we took this analytic prescription that I showed you before from Gunn and Gott 72, and we essentially blended this into the phase space diagram. So we took the run pressure characterization. We characterize run pressure essentially from modeling the density of the ICM and from using the line of sight velocities of the galaxies. And we modeled the galaxies as disks with stars and gas, essentially, exponential disks. And we blended this into phase space, and you get a region that roughly corresponds to this green triangle. And it makes sense because run pressure goes with the square of the velocity. So, at a given distance, the more velocity you have, the more stripped it will be. So that was the cartoon. This is the real comparison. On the left, we have simulations. So these are n-body cosmological simulations where we added this analytical prescription of run pressure to all the halos, and we predicted at any given position in phase space, what's the probability of a given galaxy of being stripped down to the detection limit of our body survey. And we got basically that galaxies to the right of this black line would be stripped. And if we go to our observations on the right-hand side, here are the observations for Able 963, which I showed before. All the dots are cluster members and the blue squares are gas-rich galaxies detected in H1. And you see that the resemblance with the prediction is quite remarkable. All the gas-rich galaxies are outside this region. And inside the stripping zone predicted by simulations, we essentially don't detect any H1. So what this first exercise proved is that phase space is really useful to trace fast cluster processes such as round pressure stripping, which is something that happens on first infall in the orbit of a galaxy that just came into the cluster. We've done a lot of follow-up work based on these results. One of the things we did was, well, I went back to the Virgo cluster and it's like, okay, but how do galaxies look in the different regions of phase space? And for this, we needed the resolution that we could only get nearby. So together with Avi Chung and her group, we looked at the Viva galaxies in phase space, and we indeed found that galaxies in this part of phase space, very far from the cluster at low velocity, have very extended H1 disks, as you can see here. And we call this the pre-stripping stage. Then galaxies that are close to the cluster core, but at high velocities, are the ones that have the highest asymmetries in the H1. And this is what we call peak stripping or stripping stage, where there are actually a lot of the gas is being removed. And then at lower velocities, at intermediate distances, we found a lot of the post-strip galaxies. So galaxies that are already past pericenter and already lost a lot of their gas. So we could really date and track this process happening to all of the galaxies in this cluster quite well. Now, I'm going to turn now into optical and UV observations of galaxies in clusters that tell us a complementary story of round pressure stripping. So in the last decades, we've seen a lot of papers commenting on examples of these so-called jellyfish galaxies in the optical and UV, where you have this, for example, this galaxy is a beautiful spiral galaxy with very long tails or tentacles that have knots of star-forming pockets in these strip tails, okay? In some cases, you have warped galaxies that look like a U, and these features are typically found opposite the direction of the cluster center, as these arrows here indicate. And in some cases, there have been narrowband H-alpha observations. In this case, it's a coma galaxy observed with HST, and on the right-hand side, it's a galaxy in the Norma cluster observed with the MUSE integral field spectrograph. And the H-alpha emission is shown in red, and this is essentially showing that the ionized gas can be a very extended component of the strip galaxies that we don't easily see in broadband optical images. This case in particular, the 100 in coma, it's a very long tail, 60 kiloparsecs long, and very collimated tail as well. And we will see later how this collimation can be explained with magnetic fields. So we published the largest sample of round pressure strip galaxies a few years back in 2016. Actually, another paper by McPartland et al. Also came out that year, because so far there were only a few of these galaxies in the literature. And we started compiling bigger numbers. This paper had over 400 jellyfish galaxies in different environments, so in the field even, and in clusters of different masses. And we decided to follow them up with MUSE, okay? So we got 120 hours of MUSE time to follow over 100 of these jellyfish galaxies. And the great thing about MUSE, for those of you that don't know this instrument, is that it's an integral field spectrograph that gives us a lot of information. It essentially gives us 90,000 spectra in one go. So it's a data cube where we can extract spatially resolved spectra for these galaxies. These are the first 50 galaxies observed by GASP, as seen in reconstructed broadband images from the MUSE data cubes. And you can see some of the round pressure strip features that we detected in the parent sample from optical images. But this is only the tip of the iceberg. When you look at H-alpha, is where you really see these very extended tails of strip material that I commented before. So this is the largest sample of detailed observations of jellyfish galaxies ever made. And we can extract a lot of information from this extremely beautiful data. So I'm going to show you here one example. This is the galaxy that we used in the first GASP paper to showcase the survey. It's a galaxy falling into this galaxy cluster. You have here the BCG. And the tail was so long that we used 2 MUSE pointings. And with MUSE, we can look at a lot of things that I'm not going to go into the details of, but essentially, we can look at how the gas and the stars are moving in these galaxies. Here you have the gas kinematics showing clear rotation that holds out to the outer tails. We can also look at the velocity dispersion of the gas, that it's much lower in these knots of star formation. We can do BPT diagnostics, so line ratios to determine what's ionizing the gas in the different parts of the galaxy. So for example, gas that is being ionized by star formation is colored in red and mapped here in the galaxy, and gas that is being that comes from an AGN is here at the center. We can also look at metallicities in these galaxies, gas phase metallicities, ionization parameters, age of the stellar population, a lot of things. It's really infinite the amount of things that you can do. And I'm not going to show you individual results, but kind of like more statistical analysis that we've done of the broad population of gas jellyfish galaxies that we have separated into essentially 4 different classes that have been evolving a bit with time, but they're mostly mild cases of stripping, like I show here, extreme examples of stripping, where we have strip tails that are longer than the stellar body of the galaxy. And we have these truncated profiles or post-stripping cases where you have that the stellar disk, which is this red contours here, have already been stripped of the gas, and you only have a little bit of gas here shown in the color bar. And then we have some cases where we don't really know what's happening, that, you know, there seems to be some kind of multi-directional effect changing this galaxy's appearance, okay? So one of the first things that I particularly wanted to see was to see if we could also see in the optical this evolution of stripping in the phase space diagram. And this is shown here on the left. So in the background, you have all the cluster galaxies from the parent sample of GASP. And the stars correspond to the gas jellyfish galaxies in the different stages of stripping. So the blue stars are initial stripping, the green stars are extreme stripping, and the purple ones are post-stripping. And you can kind of see the effect that I showed before with the Virgo galaxies, where as the deeper you go into the potential and the highest the velocities, essentially, you get this extremely long strip tails. So there's incremental stripping as they approach pericenter. And the other thing we found is that the velocity dispersion of this population of galaxy is much higher than even star-forming galaxies in clusters. And this means that jellyfish galaxies are preferentially on radial orbits. So they go very fast, very close to the cluster center, which are, of course, ideal conditions for stripping to happen. So it makes sense that in order to get these extreme features, maybe you have to have very plunging orbits. And this is consistent with some work that has been done. This is work in the literature from Roberts et al. 2020, where they plot the direction of the tails of strip galaxies within the coma cluster. And they find that most of the tails of jellyfish galaxies point away from the cluster center. And this means that indeed, all of these galaxies are essentially falling into the cluster for the first time. So we're working on a statistical analysis of tail directions in different clusters, actually, with Rory Smith, where we want to put numbers to this. We want to constrain what is the lifetime of tails in different wavelengths as well, because this distribution can tell us a lot of information about that. I'm going to just show some highlights from the GASP survey. So one of the highlights that we had was an unknown, completely unexpected result that we found from the 7 GASP galaxies that had these extremely long tails that were longer than the stellar body of the galaxy, we started finding that many of them had an AGN. And in fact, 6 out of the 7 GASP galaxies with extreme tails that were observed by the time this paper got published had an AGN. So the fraction was extremely high. So almost all of these extremely stripped galaxies had an AGN. And although the numbers are, of course, very low, 7 galaxies is not a lot, the fraction is very impressive, considering that AGN are quite a rare population overall. You only get about 3% of AGN in clusters and about 8% in the field, which is not much higher, while we get 6 out of 7 in GASP. So we think that somehow RAM pressure stripping is not only removing gas from the disks of galaxies, but is helping gas to be funneled into the center, triggering the nuclear activity. And we had the chicken and egg problem. We didn't know if maybe the AGN was aiding RAM pressure or RAM pressure was aiding or fueling the AGN. And when you look at these galaxies in phase space, you really see that they're all the AGN in this sample are in the region where you expect stripping to be very intense. So we really think RAM pressure is helping the supermassive black hole to grow. And there is supporting evidence from other observational work and also simulations. In terms of star formation, what we've learned, I'm gonna just very summarize it here. There's over 30 papers in GASP now, and with a lot of details in this if you want to go into the details, but mainly we see these different features. We have galaxies, many galaxies have what we call the leading edge or shock front, which has a kind of half ring of star-forming knots. And this is the side of the galaxy that is interacting with the ICM. Opposite to this side of the galaxy, we have the stripped tails. And this indicates that the galaxy in this case is going from left to right in your screen. Towards the cluster center. And within the stripped tails, we have 2 components. We have knots of star formation. These are bright star-forming clumps that formed in situ from the stripped tails. And the masses of these clumps are comparable to ultra-compact dwarf galaxies and to globular clusters, which is interesting to think about. How you can form these kind of objects outside the main body of the galaxy. And you also, in addition to the clumps, we have this diffuse component that it's ionized by star formation and also composite liner-like emission, which is also very interesting. And there's papers coming out that talk about this diffuse component in the gas galaxies. And if we look at the galaxy disk, we find that there is a significant but mild, I would say, enhancement of star formation in many of these galaxies, okay? So here there's a paper by Benedetta Vulcani where she shows nicely that for all the gas galaxies, here are color-coded by different kind of intensity of stripping, have slightly elevated star formation rates with compared to a control sample of non-stripped galaxies. And this is only looking at the disk, okay? But as you can see, there's a lot of scatter, and it's not like it's a huge increase, but it's definitely a significant one. Another thing that we've seen pretty clearly with this data set is that stripping occurs from the outside of galaxies towards the center, as I showed with the simulations at the start of the talk. Here you have one of our jellyfish galaxies where you can see the stellar component in white and the ionized gas, the H-alpha, in red. And you can see that some of the outer parts of the disk are already devoid of H-alpha. And if we look at the spectra from the MUSE data cube in different regions, we find that, yeah, in these star-forming clumps, we have a typical star-forming spectra with this very nice bright emission lines. At the center of the galaxy, we have the AGN, we have this broad emission. And in this region where we think is the transformation really at play, like you just strip the gas, we look at the spectra there and you actually see spectra typical of post-starburst galaxies. So these are post-starburst features. And these have been observed through the disks of non-star-forming galaxies in clusters that have recently been stripped. So we think that this is what happens as you strip the disk from the outside in, you start quenching the galaxy also from the outside in. Another evidence for this outside-in stripping comes from metallicity gradients. Here I show one example. Where if we look at the gas phase metallicity across this stripped galaxy, you have lower values are darker and higher values in yellow. And we can essentially trace the radius of the galaxy or the rings of galaxy that were stripped first. So we have in this very long tail, essentially the same metallicity, which we associate with the outer part of the galaxy that got stripped first. So here it's a different view of the same thing. You have the metallicity plotted as distance from the cluster center, and you have the lowest metallicities at the outer parts. Another interesting result that came out recently from a paper by Callum Bellhouse is the finding, another unexpected finding that we started seeing in some of these galaxies, actually in these galaxies where we saw it first. Evidence that the spiral arms of these stripped spiral galaxies are being unwound or broadened, if you like. And actually, it makes sense. We did some simulations to understand exactly what is happening. And in the simulations, we looked at essentially two cases with some variation. So edge-on stripping, so where the galaxy falls edge-on towards the cluster center, and face-on stripping, where you have a face-on encounter between the galaxy disk and the intercluster medium. And in both cases, we see this effect of unwinding. So on the left, we have observations from the GASP survey and color-coded by the velocity of the H-alpha component. And on the right, we have simulated galaxies in these two different scenarios, where we can reproduce really quite well the observed properties of these galaxies. So in the edge-on stripping, we have essentially differential ramp pressure, which is caused by the rotation of the disk, which slows down and piles up the stripped material. And in the face-on case, we have that the gas is removed from the outer parts of the edges of the galaxy, and this falls into higher orbits, and they appear to unwind, trailing behind the galaxy. I'm out of time, but I'll just show this one last result, and I'll skip to the conclusions. This is a very exciting result by Ankla Muller, published last year, where she finds large-scale magnetic fields in one of these beautiful jellyfish galaxies from our survey, one that I showed at the beginning of the talk. And these magnetic fields are very ordered lines. These are the magnetic field lines, which, as you can see, are parallel to the stripping direction. They coincide with the tails. They're very collimated. And essentially, with high-resolution simulations, what we think is happening is that drop magnetized plasma from the ICM is essentially condensating into the external layers of these tails, where it's compressed and sheared. And we think that somehow these magnetic fields are helping in situ star formation occur. They're essentially shielding this region so that they can form new stars. Because if we didn't have magnetic fields, it would be much harder to have star-forming clumps in this galaxy. So I think magnetic fields, it's kind of like the window that we'll keep exploring for this kind of physics. It helps explain the tails in the different wavelengths, and it also helps explain the funneling of gas towards the center of where the black holes are. So definitely interesting. I'm going to skip and go to the conclusions, if my slide allows. I wanted to talk about other things, but it's a little bit late. Feel free to ask me later. So here's my summary. I hope I convinced you that ramp pressure stripping is a very important environmental effect, removing gas and transforming galaxies in dense environments. It's a very fast process that affects essentially all galaxies in one degree or another. And these jellyfish galaxies are really unique because they trace cosmic migrations and transformations at play. They're galaxies in the act of transforming. And we learned from the bodies of these galaxies that stripping occurs outside in, that you can have enhanced star formation for a period of time within the disk of the galaxy. You can feed and grow the supermassive black hole in the center. You can unwind the spiral arms. And from the tails, we can have in situ star formation in the tails, in these knots. We have highly ordered magnetic fields that help the star formation to happen. We have a very complex interaction and mixing with the intercluster medium, which I didn't show. And also through these galaxies, we help build the intracluster layer. Okay, so to understand a lot of I think the next step is to build larger samples of these galaxies to understand statistically a lot of these processes. And GASP was a first step, but hopefully we can continue doing this. Thanks a lot. I'm sorry if I spoke a bit longer.
Thank you very much for your very didactical talk, Yara. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them on the YouTube channel chat. We'll be back next week with a seminar on dark matter at the distant universe with galaxy clusters strong lensing. Goodbye. And now we go to the breakout rooms.